Okay, first of all, thank you for giving me this opportunity to talk about what was launched by the events of the few years ago by launch of this Chinese satellite has started a new, what we call quantum space race. And I would like to talk a little bit about what has been happening in the quantum area from the early days and where we are and what the road ahead is, as my title states. So I want to begin by recapping a brief, somewhat incomplete history of what we call quantum 2.0. And oftentimes we define quantum 2.0 as going beyond the understanding of quantum superposition and measurement, which is the quantum 1.0, where utilizing different measurements, we try to work at the quantum classical boundary. Of course, in 1982, Feynman proposed quantum computing to simulate quantum electrodynamic applications. That's a scientific application. Along the way, in 1984, Bennett and Broussard proposed PV84 QKD protocol. In 91, entanglement-based QKD was introduced by Eckert. And then, of course, by Bennett and co-workers in 93, invented the quantum teleportation protocol, which has played a major role in connecting several qubits together and unleashing the power of quantum XYZ technologies, including computing, simulation, communication, and so forth. In 94, Shor invented the quantum factoring algorithm. And of course, in the early 90s, as you know, e-commerce was taking off. And the Shor factoring algorithm, by making it more efficient to factorize large numbers, threatened this growing e-commerce based on the RSA algorithm. And that, in a way, launched the race to build a quantum computer. And we've heard today the status of where things are in various aspects of quantum computing and how their near-term applications might impact the finance community. And that's the forum for today. Of course, along the way, quantum error correction and fault tolerance concepts were introduced right after in the mid-90s. And it led to roughly a 15-year period of very intensive activity. And along the way, one discovered that realization of a Shor factorizer actually is quite difficult. Getting qubits of high quality, and we've heard today a lot of status reports on various different technologies that creating a large scale quantum volume where you have a large number of qubits of adequate coherence to do some useful quantum task is rather difficult. So in the circa 2010, the emphasis then shifted back to more scientific applications, which was the original motivation by Feynman to introduce quantum computing. And in a way, the Shor factorizer kind of hijacked this field of quantum computing to just factorization, as opposed to looking at the problems in more general space in terms of perhaps scientific simulation, optimization, and so forth. And since 2010, the focus has shifted back to, and we've heard today, a lot of the applications that Fred Chong talked about and some of the others in terms of their use in financial system optimization and so forth. And since about 2015 or so, the public and private investments in quantum computing have really taken off. Several companies have announced large quantum computing programs. A lot of private capital has gone into this. And on the communication side, even though the focus of the early work was on quantum key distribution, it has shifted to quantum communications in general. So I want to take a minute here to delineate the distinction. In QKD, one is trying to create a shared secret by means of quantum resources between two parties. The two parties then use the QKD to typically use another conventional encryption protocol to encrypt data. So for example, QKD could yield keys that the two parties will create session keys, and then they use conventional, perhaps AES to do high-speed communications. On the other hand, provable security is obtained by use of what's known as the one-time pad. But in order to keep up with the data rates of communications one needs today, the demands on the QKD generated keys becomes pretty stringent. In order to see what those limits are, typically in a QKD system, one is limited by what's known as the rate distance bottleneck. So that means that you can get secure key generation rates of perhaps tens of megabits per second, but you can only do it over a few kilometer type distances. Or you can go, perhaps the record is a few hundred kilometers these days, but then your secure key rate is limited to perhaps tens of bits to kilobits per second. And in order for secure communication or quantum communication in general, where one is trying to go beyond just simply exchanging keys to do secure communication, but perhaps interlinking different quantum resources together, one needs to look at what has been the history of classical communications. And here, of course, since communicating over long distances requires qubits that can move around at the speed of light. So often one talks about, in comparison, the state of the art in optical communications or transparent optical networking. So judging, let's recall what the history of that has been. Again, optical communications started to take off in the late 70s when low loss optical fibers came on the scene. Early days, distances were limited by losses. Again, even though the fiber is highly transparent, but nevertheless, there is a little bit of a loss that occurs. Roughly 4% of the light is lost every kilometer of propagation in the fiber. So in the early days, the distances were limited by this loss. And then invention of the optical amplifier more or less changed everything. The exponentially decaying signal-to-noise ratio, SNR, was periodically amplified by means of these amplifiers, and the whole fiber line, the SNR, instead of exponentially decaying, started to change into a linear degradation, which enabled global reach. And along the way came wavelength division multiplexing, WDM technologies, and electronic mitigation techniques of channel impairments. That was another big step that led to the global connectivity that we have. And then interfaces to wireless systems to have handheld devices with which we can globally not only communicate, but also access systems on the cloud to do ubiquitous computing as well. So one can ask the question, if we are to do, instead of classical communication and classical computing, go to a distributed, ubiquitously available quantum communication and quantum computing, then can similar things be done with quantum communications? That is, can we progress quantum communications networking to the level that is similar to the history here for classical communications? And in order to overcome this rate distance bottleneck, two approaches have been followed. One is based on trusted satellite, and the other is quantum repeaters. And of course, I wouldn't have time to say much about quantum repeaters because a lot of work is still ongoing, and one needs to demonstrate a working quantum repeater in the lab yet. But this approach of trusted satellite is the one that ushered in this modern era or modern stream of funding around the world, which, as I mentioned before, back in 2015, China launched this satellite called MISSIUS. As you may have read in my biography, I was a program manager at DARPA for 4 years. And in 2015, when that satellite was launched, it caused a lot of consternation in the DoD circles. And particularly when in 2016, this shown on the left here, is a QKD entanglement. They did a whole bunch of experiments, but this one noted here is a distribution of entanglement over 1,200 kilometers of fiber. And as I said before, the losses over 1,200 kilometers of fibers are such that it would be almost impossible to have any secure key rate. On the other hand, by giving trust to this satellite and doing separate key distribution and then using XORing those different distributed key streams, one was able to breach beyond this limit of direct fiber connections that is possible to go over a few hundred kilometers, as I mentioned before. The point here to make is that there was a lot of work on QKD and entanglement distribution that was done in the US in the decade before, circa 2000 to 2010. However, we failed to engineer our systems because of lack of investments or there are a number of reasons. But the point here is that the Chinese took the technology that was developed. So shown here is the source of entanglement that is on board that satellite MISSIUS. This is a source of entanglement based on a periodically poled crystal that was developed under a IARPA program, back then ARDA, program in the US. So the Chinese took the US developed technology and engineered it to the point so they could put it onto a satellite and then demonstrate these hero experiments that show the capability of global key distribution. Of course, they have done many other hero experiments along the way, for example, doing quantum encrypted phone calls between two different continents and so forth. Back in around 2000, my lab here in Chicago at Northwestern University was interested in utilizing the same kind of nonlinearities, that is optical fibers, to create entangled photon pairs to distribute entanglement or to do quantum communications over long distances. And what we showed in the early work at the turn of the century, around 2002 and 2005, and even patented a source of entangled photon pairs that utilizes essentially ordinary fibers to show that one can create entangled photon pairs directly in the telecom band of the fiber and distribute those photon pairs over long distances. And this work was also turned into a post-deadline paper. This is dating back to 2006 timeframe, where we used this fiber-based source of entangled photon pairs and demonstrated, as I said, back 15 years ago, that you can do direct entanglement distribution over fibers that are 100 kilometers, 50 kilometers on each side. So you can do entanglement distribution over distances that are 100 kilometers apart in the presence of classical data. So for example, signal and idler photon pairs go through these 50 kilometer spools of fiber, which have the standard 10 gigabit per second telecommunication signals flowing through them, and demonstrate that coexistence of classical and quantum data is possible. This technology was commercialized through a company, NewCrypt, that is showcasing at this event as well. And more recently, people at the Army Research Laboratory are utilizing the instrumentation developed by NewCrypt in their own cybersecurity and quantum research experiments. So this is a news release that dates back a couple of years. So the point here is that, yes, perhaps some of the commercialization activities and developing technology and creating the quantum ecosystem that was our goal in the early 2000s, perhaps it was a bit ahead of its time. And it is time to catch up and bring quantum technologies in a more aggressive fashion in the Chicagoland area. Again, the same type of fiber-based, this spontaneous four-way mixing source was utilized by the Chinese in demonstrating their quantum teleportation experiments and over installed fiber base in the Beijing area. So once again, the Chinese took the technology that was developed in the US and turned that into demonstrators that have given a tremendous visibility and in some ways has spawned the new quantum space race that the title of my talk points to. They also, in the very same paper, they also talk about a quantum network. And the notion of quantum networks also dates back to the early 2000s. My colleagues at MIT and at Northwestern proposed the infrastructure for a quantum internet. And of course, Jeff Kimball in 2008 pioneered conceptually what a quantum internet might look like. Of course, along the way, there are tremendous technical challenges that still remain in order to have this notion of a quantum internet. So I've listed here a few of them. So for example, how would we architect a quantum internet? What would the architecture be? What would be the protocols and what would be the algorithms? Would it have a layered structure, much like the classical network? And then how would these layers be determined? Would entanglement distribution be a separate layer? How would quantum channels and classical channels coexist? After all, classical communication is a necessary part of that quantum teleportation protocol. Furthermore, how would we control and operationalize a quantum network? How do we share quantum channels among the various users? What's the best way to distribute quantum entanglement? Would there be entanglement factories which will behave like quantum ISPs? And what about quality of service? And how will we measure entanglement as it is being distributed? And what would be the software designs and of course the control algorithms that would be needed to manage this quantum network. So in this regard, two recent DOE workshops have emphasized, one happened in 2018 and the other one was just this year, which emphasized the urgent need for developing the science and technology of quantum networking. And these, if you Google these reports of these DOE workshops are available on the internet. One of them was unveiled at the Chicago as part of the Chicago Quantum Initiative, and Governor Pritzker mentioned earlier today about that unveiling of the quantum networking blueprint. As part of the first workshop of 2018, there was a small program that was launched as sort of a pilot project, and Northwestern is participant in a Fermi-led program, what we call IQNet, or Illinois Express Quantum Network, which aims to demonstrate entanglement distribution and teleportation over installed fibers, and also on the Northwestern end, connecting the Northwestern Evanston campus and the Chicago campus to demonstrate the coexistence of classical and quantum channels, as we had done in the laboratory in the example I mentioned before. Other partners in this project led by Fermilab are Caltech, Argonne, NuCrypt, the company I mentioned, and Hyperlight, that's another startup company coming out of Harvard University in Boston, in Cambridge. Here is a kind of a physical overview of the network that we envision. It's 6 sites, 4 of them on the east leg and 2 on the sort of the west leg, connecting Fermilab and Argonne. And this is the beginning stages of a network that we hope to establish in the Chicagoland area. This would be one of the first metro scale networks doing standard quantum communications, including teleportation and beyond. I want to conclude by some thoughts on quantum communications in general. So there was a workshop back then when Jake Taylor was still at NIST before he took leave and went on to the Office of Science and Technology Policy. He had organized a workshop on building the foundations for quantum industry back in October of 2017. And of course, him and his colleagues at NIST at the time were thinking about this new quantum initiative that was signed into law in 2018. And in particular, Jake approached me and asked me to lead a discussion on quantum communication, in particular on some organizational thoughts in terms of how do we create a nationwide ecosystem that would commercialize quantum technologies. And here, quantum technologies means quantum XYZ very broadly, computing, communication, simulation, sensing, and so forth. And my thoughts here, I think in 3 years, they have sort of strengthened them a little bit. Quantum technologies are fragile. They need classical perfection to cross into the quantum domain. And thus they require decades-long sustained efforts. Typically, the way research is structured in US academic institutions, which have tenures of postdocs or graduate students over 3 to 5 years, that's just not enough. So academic institutions can't just do it alone. Efforts requires a much longer than those 3 to 5 year timeframes that I mentioned. We do need participation from national labs because we need to train and sustain these experts who make their careers at national labs and then become a conduit for a continuous back and forth with the academic community. And then finally, we also need industry involvement because technologies need to be, classical technologies need to be matured through the quantum domain, through the classical quantum interface into the quantum domain. And industry is needed to make that perfectly classical technology working at the quantum limits to be widely available to researchers both at the national labs and also in the academic environment. So we do need university, national labs, industry partnerships. And finally, we also need this new discipline, and that much of it has been talked about. Margaret talked about it, and earlier Fred talked about it, and Brian also talked about the educational aspects of all the funding that is being made available in these new initiatives. One needs to create this new type of quantum engineering as a discipline. It's an interdisciplinary effort between physics, engineering, computer science, and in my view, an application field. And in engineering, of course, electrical and computer engineering play a major role. One needs to, this application field could be what would create the pull. It could be optimization as an example. Today we're talking about in finance applications, or it could be some kind of a chemical reaction being optimized, and the domain could be chemistry, or domain could be material science. So we do need to work towards creating a new cohort of these quantum engineers who would work in this future quantum industry and make these kind of new technologies. The realization of quantum 2.0 will require these kind of transdisciplinary efforts. And finally, we do need longer funding streams, and the launch of these many national quantum initiatives, both from DOE and NSF, is a step in the right direction. I think I want to stop here.